Okay, hi there. This is Dr. Matthew J. Trom. I am going to present to you on the parameterization of customer needs. So let's start with a definition for the word parameterize, which means to quantify in numbers. We are engineers, and we like to think in quantitative terms and numerical terms. And so this process essentially removes all ambiguity from problems, and it converts the customer language into an engineering language that then allows us to quantify and bound the problem. So typically, if you're a design engineer, you interact with clients who are not technical people, but you're designing products for them. And so they will typically give you a series of needs and requirements for their product that are not quantitative. So it's your job to convert them from a customer need statement into a series of quantitative metrics. So I think the best way to explain this is to just give you an example. And so I pulled from the annals of history a quote from Henry Ford, who hopefully created the basically modern assembly line for automobiles and modernized the automotive industry in the early 20th century. Um, and there's a quote attributed to him, which is essentially, quote, if I had asked people what they wanted, they would have said a faster horse. Henry Ford. And so I thought it would be fun as an example to take this quote and use it as a customer need and walk through how to convert a very qualitative customer need into a quantitative metric that's useful for engineering design. And so the place to start, I think, is to break down this customer need and kind of annotate what's wrong with it. So, I've underlined kind of all those issues and then added some comments here. So, first one is the customer saying, "I want a horse." Well, is it really a horse that you want? As Henry Ford said, that the customer didn't realize that they wanted something better than a horse until that's what they were shown. And so in engineering design, we try to eliminate specificity as much as possible in the customer need statement to fully open and allow exploration of the design space. So unless you really want a horse and that's the only thing that you'll tolerate, we want to get rid of this word and make it more general. So that's one. Number two, this person wants a horse that goes significantly faster. So the word goes is problematic because what does that actually mean? It's very kind of arbitrary. So we need to kind of clarify and quantify what that means by goes. And then significantly faster. So how do you define significantly? Is this 5% faster than a horse, 10% faster, 100% faster? Who knows, right? So significantly doesn't mean anything until you assign a number to it. And then faster, um, it- how much? Faster than what? Is this faster than a current horse? Is this faster than a person can walk? So there's a lot of kind of arbitrariness here that we need to address. And then kind of the biggest problem with this is that this customer requirement fails to mention the primary goal of the horse, which is to carry a human rider, right? This is a transportation application. So you could imagine actually meeting all these requirements with a horse that's like a miniature horse. It's like super tiny, right? That a person couldn't actually sit on and use for transportation. So there's an unstated requirement, which is just assumed or implied by the customer that we need to add to make it, truly an appropriate engineering set of quantitative metrics. So here's how I rewrote it. We're looking for a solution that should carry a human 50 miles with a top speed of no less than 20 miles an hour. And how do you come up with these numbers and this quantification? Well, some of it is research. So you go out and do your own research to come up with the numbers. And some of it is talking to the customer and getting the customer to commit to certain values. So I did that same sort of annotation here where I underlined the things that I corrected and then kind of described why they're better. And so instead of a horse, we now have a solution. So that eliminates the constraint of being locked into a horse. We have a solution that's carrying a human, right? So that gives a sense of the function of this thing. It's a transportation solution for human beings, so a human has to fit into it. Um, it now goes a distance which is 50 miles. And the way that I came up with 50 miles is I went back and looked at the old US Pony Express system, which would typically run horses about 35 to 45 miles between stations before they stopped to rest and the courier would switch horses. And so I figured we're not going to have this horse run or this car or whatever it is run at an all-out sprint for the entire distance. So I, arbitrarily added about 5 miles to the upper bound of what the Pony Express used to give me a nice round number of 50 miles, right? So this solution now has to go 50 miles with a person sitting on it. And then instead of just substantially faster, we actually quantify a speed, right? So with a top speed of no less than 20 miles an hour. So faster is clarified relative to the speed of a horse, and the desired direction is given, right? So it's better to go faster rather than to go slower, right? You want to go no less than 20 miles an hour, but faster is better. So looking at this is a better need statement than the one that we had before because it's more clear and more quantitative. However, there are actually three different requirements, at least three different requirements in this one sentence. And so this really should be split into three different needs. And the reason for that is because typically in engineering design, you want to decouple your parameters as much as possible, right? So this allows you to essentially solve for A, well, B is independent, and then solve for B, well, A is independent. And if you've decoupled A from B, you can solve those two problems independently with two different concepts. If you've got everything coupled together, like I have in this paragraph, you're basically generating one concept that has to do all these things, and maybe you come up with something that can go 50 miles an hour, but it can't achieve, or it can go 50 miles, but it can't achieve 20 miles per hour. Right. So you need to decouple these things to be able to kind of fully explore and exploit your design space. So a great example of this is a shower faucet. So shower faucets typically have a single handle, and that handle controls both the volume flow rate of water and the temperature. And so in this case, the situation here on the left, if you wanted to get a large volume flow rate of cold water, you couldn't do that because you have to turn this handle to get large volume flow rate. And as you're turning it counterclockwise, you're getting hotter and hotter and hotter. As the volume flow rate goes up, the temperature goes up. So temperature and volume flow rate are coupled in this situation, and there are combinations of flow rate and temperature that you can't achieve with this single handle controller. So a better approach to decouple those parameters, temperature and volume flow rate, is to have two different handles, right? So one handle controls the volume flow rate and the other handle controls the temperature. And if those two are decoupled, now you can get any combination of temperature and volume flow rate. So you have a better access to the entire design space. So that's what decoupling does for us as we're generating these kind of engineering appropriate need statements. Um, so what I show here um, is basically my first cut at this, right? Where I take my initial need statement, which is I want a horse that goes significantly faster, and I walk it through a series of fixes, which I've outlined here, to get my final requirement, which is the solution should carry a human 50 miles with a top speed no less than 20 miles an hour. So that's pretty good, right? But I can do even better by decoupling the parameters in this statement into three separate requirements. So originally this was one need, and now I've got three separate needs that I'll just call 1A, 1B, and 1C to differentiate them from each other. And the three are the solution should carry a human. Um, that's 1A. 1B is the solution should travel 50 miles. And 1C is the solution should have a top speed of no less than 20 miles per hour. So now that those three are separated, you are able to come up with subsystem concepts for each of those needs separate from each other. They're not coupled together anymore. And you should be able to produce a better overall design as a result of decoupling them. The last thing that I want to mention is sometimes you'll get a customer need that is already quantitative. So cost is typically an example of this that you get even with non-technical customers. So we're talking about, basically a horse replacement, so an automobile. And so you might imagine a need that is something like the final cost should not exceed $40,000, right? It's a sort of mid-range, maybe sort of semi-luxury type automobile. You could probably get for about $40,000, and that's already a number, right? And it already has a direction associated with it. Should not exceed $40,000. So, as the engineer evaluating this need, you don't need to mess with it. You don't need to change it. Just leave it the way it is. And so it can just propagate through into the final version of the customer need statement as it was originally stated. The reason that I bring up cost is because cost is typically a source of confusion for students as they're walking through the design process, in that you really have to be careful that you understand what the customer means by final cost. And there's a couple of different ways to interpret, at least four. So final cost could mean the cost of materials to build the prototype, right? Basically, what the customer is paying you as the design engineer to design and build. Maybe that's $40,000. It could also mean that cost to produce a bootstrap prototype, which is essentially you're working in your garage, and so you're minimizing costs as much as possible, but you still do have to pay for the materials and any outsourced labor, for example, assembly or fabrication labor. So that's the second way. A third possible way to define cost is a cost per unit for a minimum viable product, fabricated as part of a small batch production run, right? So you're ready to beta test and hand products to customers. In that case, you still have to pay for labor and materials like you did before, but now potentially you've got a company and you're paying for salaries and overhead, right? In a space where you're doing this manufacturing and assembly. And then the fourth possibility is the cost per unit that the customer sees when they buy this thing commercially, this product commercially. So that includes all the previous costs, right? Materials, labor, salaries, and overhead, and an additional profit margin, which you have to build in to keep your company competitive with respect to ongoing research and development. So, really important to clarify with your customer when they say final cost must be or must not exceed some value, what the customer means. So, in this case, I said, $40,000 is the cost for kind of a medium to kind of semi-luxury range car. And so I would interpret this $40,000 as this last one, cost per unit for commercial sale. This is the actual sticker price of a car sitting in a dealership in, the late 2020s. Um, so that's how I would interpret it. But again, you have to talk to the customer to make sure that as the design engineer, you understand what the customer's expectations are for their needs, even if those needs are quantified. Okay, so that brings us to the end of the section on parameterization of customer needs. Thank you for your attention.